We see stars, galaxies, nebulae, but most of the universe is invisible. Roughly 95% of everything out there, dark matter and dark energy, can't be seen, touched, or explained. We know it's there only by what it does. And now, for the first time, we're beginning to map it. This is the Euclid Space Telescope, a European Space Agency mission launched to chart the unseen scaffolding of the cosmos. Not to look at stars, but to trace the gravitational fingerprints left behind by dark matter, to measure how space itself stretches and bends over time. In early 2025, Euclid released its first set of data: millions of galaxies, hundreds of gravitational lenses, and the beginnings of something much bigger: a map of the invisible universe. In this episode of Scientific Facts, we'll explore what Euclid is, how it works, and why the structure it's revealing could change our understanding of the cosmos and the forces that shape it. The more we've uncovered about the universe, the more we realize how little we truly know. Everything we see, stars, planets, dust, entire galaxies, makes up only 5% of the cosmos. The rest is hidden. About 27% is what we call dark matter, a mysterious substance we can't see or touch. It doesn't shine, it doesn't absorb light, and yet its gravity shapes galaxies, bends starlight, and binds the universe together. Then there's dark energy, an even stranger force, making up nearly 70% of everything. It's not just out there, it's active. It's causing the universe to expand faster and faster, pulling galaxies apart across the void. And we didn't even know it existed until the late 1990s, when distant supernovae appeared dimmer than expected. That one clue rewrote our understanding of the cosmos. But here's the problem: we don't know what dark energy is. We don't know what dark matter is made of. And yet, together, they shape the universe, its structure, its history, and its ultimate fate. Will the cosmos keep expanding forever? Slow down? Tear itself apart? To answer that, we need more than theory. We need a map. The Euclid Space Telescope was built to chart the invisible, to trace how unseen matter bends light across billions of galaxies, and how space itself stretches over time. By observing the subtle distortions in distant galaxies, Euclid will reveal the structure beneath the stars, a structure we've never seen until now. To map the invisible, you need more than a powerful telescope. You need precision, stability, and vision on a cosmic scale. The Euclid Space Telescope was launched by the European Space Agency in 2023 and now orbits around Lagrange Point 2, a gravitationally balanced zone 1.5 million kilometers from Earth. Quiet, dark, and ideal for deep space observation. Euclid's goal is simple but ambitious: to create a 3D map of the universe by observing billions of galaxies, stretching out over 10 billion light-years. It does this using two main instruments. First, a visible imager, VIS, a 600-megapixel camera designed to measure galaxy shapes with extreme precision. It detects tiny distortions caused by gravitational lensing, the warping of light by mass, including dark matter. Second, a near-infrared spectrometer and photometer, NISP, which captures the redshift of each galaxy, telling us how far away it is and how fast the universe is expanding at that point in time. Together, they don't just show us where galaxies are, they show us how space itself bends, stretches, and evolves between them. Euclid also has a remarkably wide field of view. Each image covers an area of sky larger than 2 full moons. Over the next 6 years, it will scan more than a third of the sky, collecting the data needed to build one of the most detailed cosmological maps in history. And it's not just about beautiful images. The real power of Euclid is in the patterns, how galaxies cluster, how light curves around invisible mass, and how expansion changes with time. Because hidden in those patterns are the fingerprints of the universe's most elusive forces. In early 2025, just months after its full calibration, Euclid delivered its first major release, and the results were staggering. Over 26 million galaxies mapped in exquisite detail. More than 1,500 strong gravitational lens candidates, where massive invisible structures warp space like magnifying glass curves. Even a few near-perfect Einstein rings, full circles of distorted light created when galaxies align across billions of light years. And that's just the beginning. Euclid's early data also revealed new maps of dark matter distribution, constructed by tracing the subtle distortions in the shapes of distant galaxies. These maps don't show stars, they show gravity itself. And they're helping us visualize where dark matter is hiding in the cosmic web. In one case, scientists identified a region where the lensing was unexpectedly strong, suggesting either a massive concentration of dark matter or something else we don't yet understand. But beyond any single discovery, Euclid's early data proved its power. Its ability to scan vast areas of sky with precision, to catch the invisible by watching how it shapes the visible, and to build the most detailed gravitational maps ever assembled. And this is just a fraction of its 6-year mission. With each new data release, we'll get clearer pictures of how galaxies clump together, how space bends, and how fast the universe is still expanding. We're not just looking deeper into space. We're starting to see the structure beneath it. In its first few months, Euclid gave us millions of galaxies. By the end of its mission, it will have mapped over 2 billion, spanning more than 10 billion years of cosmic history. But it's not just building a map, it's building a timeline. By comparing galaxies at different distances, and therefore different ages, Euclid lets us watch how structure forms over time, how galaxies clump, how space stretches, and how dark energy's influence may have changed along the way. This is where theory gets tested. Is the universe expanding at a constant rate? Is dark energy really uniform? Or are there hidden shifts that challenge the foundation of our models? Some predictions suggest Euclid may even detect subtle deviations in gravity, hints that Einstein's equations, so far unshaken, may need an update. And as its maps grow, so will the questions. Where is dark matter most concentrated? Why do some galaxies seem to sit in empty space, while others cling to invisible threads? There's only one way to find out, and Euclid has 6 more years to keep looking. Most of what shapes our universe can't be seen. Not with our eyes, not with ordinary telescopes. For decades, we mapped the stars without ever knowing what held them in place. We saw galaxies, but not the gravity that bound them. We measured expansion, but couldn't explain what was driving it. That's the world Euclid was built to explore. Not a telescope chasing beautiful pictures, but a mission to chart the structure beneath it all. The threads of dark matter that stretch across billions of light years. The silent pressure of dark energy pulling galaxies apart. With every observation, Euclid is bringing us closer to answers we've never had. And maybe closer to questions we haven't even thought to ask. Here on Scientific Facts, we'll be following those discoveries as they unfold. The small ones, the big ones, the quiet, unexpected ones. If that journey speaks to you, I'd love to have you along for what comes next. Subscribe, stay curious, and keep your eyes on the deep sky. Because the universe is still revealing itself, and we're just beginning to understand what it's trying to say.